I'm Corey. I work at Lambda, staff ML engineer. My pronouns are they, them, and I'm going to be talking about distributed training today. Everything I'm going to be talking about can be found on this GitHub repo. The QR code leads to this GitHub repo. It basically walks through, starting with like a single GPU training script, how to add data parallel all the way down to multi-dimensional 2D parallelism. So if you don't feel like paying attention, just scan this QR code and just read the guide instead. OK, so here's our agenda. I'll just give a quick background just to get us all on the same page. And then I'm going to talk about 2 data parallelism techniques. I got some live demos, super risky. And then I'm going to end off talking about some other types of parallelism. I know a lot of people have talked about all the types of parallelism, so we're just going to talk about it more. OK, what is distributed training? Normal training is just single GPU, and distributed training is anything more than that. So that could be a single node with 8 GPUs, or you could have entire clusters with like tens of thousands of GPUs. So it's really anything like that. Why would you do distributed training? It's really 2 reasons. One, to train in less time. So if you have 10 GPUs, you can train 10 times faster. The graph over here is showing the techniques I'm talking about today, where you can kind of beat linear scaling with FSDP. The other reason is if you're training foundation models, and you basically just need thousands of GPUs to do that. And we definitely get to different types of problems once we're training models that big, which I'll talk to at the end. There are a lot of different frameworks out there, Torch Titan, DeepSpeed, Megatron, to do distributed training. Here's just like some history about them. They started even before 2020, but they really kind of got popular in 2023. There's a lot of things that happened this week. This is when Llama got released. The week after, ChatGPT API got released, followed by Llama CVP and GPT-4. Like all of this happened in the span of like 2 or 3 weeks. And so everyone was kind of interested in training these open source models. And this was before LoRa, I believe. So people were actually doing like full fine tunes. OK, let's get into distributed data parallel. This is like kind of like the first technique people visit. And then I'm going to talk about how it kind of works under the hood. I'll show a little bit of a code snippet, and then I'll do a live demo. If you want more code snippets, go to the guide. I just can't talk about it all in 20 minutes. So yeah. So I'm going to go left to right on this diagram. First, with pretty much any distributed training, you split your data set across all of your GPUs. With DDP, we have a full copy of our model on every single GPU, which is very expensive, but it means you can just run the forward and backward pass completely as normal. After the backward pass, we have different sets of gradients on every GPU because we have different input data. The cool part about DDP is this all reduced mean, which basically all the GPUs like talk to each other and communicate about all the gradients. And then after that, we magically have all the gradients on all the GPUs are exactly the same. And then we have a full copy of the optimizer also on every single GPU, so we can just run optimizer as normal. So it's pretty straightforward, but it does cost a lot of memory. So how do we end up doing this all reduced mean thing in PyTorch? By just wrapping our model in distributed data parallel. I was actually surprised when I was looking into this a couple of years ago, because I thought distributed data parallel did something like way more complicated, but it literally just does the synchronizing gradients, which I will prove to you by showing you the docs, which I'm sure all of you have read very thoroughly. And if you don't believe the docs, because sometimes they're out of date, here's the actual code where it does that. OK, let's get to some live demos. Let's add some risk into this presentation. Is this big enough? Can people like read the terminal? Can't tell. No? OK. Thank you for your response. OK, anybody remember the shortcut for increasing font size off the top of your head? Command plus. Oh my gosh. Great job, team. I really prepared for this. OK, let's start off with just single GPU training. I have 8x H100 node right here. We're going to train Llama 8B. So this is just like a normal training script you would see. So we're using Hugging Face transformers, have our normal PyTorch data loader, blah, 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 blah. You guys are experts at this, I don't need to do this. So I'm just showing this just so we can start at square one. So we already started training. Let me get up NV top here. So you can see that we only have one GPU training. We're pretty much maxing out the GPU, et cetera. So let's cancel this, and I'll show you how to run distributed data parallel, which is the second chapter. Again, I'm just running the code in the guide, so if that is the real winner here. There's a lot of stuff that changed in here, but just to show you, this is where we're wrapping our model with distributed data parallel, and you can pretty much run the same exact command. You just change Python to torch run, and then you have to tell it how many GPUs you have. We're at 8. So we're gonna run this. One thing with DDP is that it has some overhead associated with it to do that all reduced mean, so it does take a little bit more memory. That is what we will see here in a second. Okay. So it started training, and you can see with distributed training, you get the output from all the different ranks that are running. Now we started, and oh shoot, an error, the live demo. Gods, what are you doing? Just kidding, it was planned, surprise. Okay, let's go back to our, okay, let's talk about 0, because in DDP, as you remember, our model and optimizer are copied on every GPU, which takes up a lot of memory, which is why we just ran out of memory, in addition to the overhead. So 0, which started with deep speed, splits the optimizer across all of your GPUs. It's really easy to add in PyTorch. It's just this one snippet, so I'm just gonna add it. We're gonna do some live coding. And now that I've satisfied the live demo gods with an error, all of this will run very smoothly. Okay. So now we can run the same exact command, and we won't run out of memory. We'll actually, it might be a surprise how much memory we save, but with Llama AB, it's like 16 gigabytes for the model weights, and then the optimizer has like 32 gigabytes of memory, so now we're splitting that evenly across our 8 GPUs. Yeah, so I'll just wait for this to succeed since it's not gonna crash anymore. Everyone cross your fingers maybe. Okay, yeah. So we have the training now, and it looks like we're sitting at like 60 gigabytes. So we have enough room to increase our batch size a bit. But that's 0. It can save you a lot of memory, and definitely if you're using DDP, I encourage you to just add it. It's literally a 2-line change. Okay, so what do we do if we still run out of memory, if our model's so big that even with 0, we need to do something else? And that's where fully sharded data parallel comes in. And it's just kind of like the next step. So 0 added in optimizer, splitting overall GPUs, and FSDP splits our model and the gradients over all the GPUs too. So it's mega memory saving. Okay, here's another high-level graphic. This is our DDP forward pass. So if you remember, all the GPUs have all the parameters in memory, and you can run forward pass in normal. FSDP just adds this bit before and after the forward pass. So we split our model parameters into shards. So each GPU just has like a small section of the model parameters. And then we do an all gather right before forward, which basically is kind of like the all reduced mean, but the opposite way. So after it, all the GPUs have all the parameters in memory. And then we run forward pass as normal. And then we reshard, which basically just means delete the shards that you're not using. So it's not conceptually that crazy. But what exactly is this like params? Like what is this block? And I'm just gonna pull up the Llama model architecture just for reference. So this can actually be pretty much anything. So it could be a single linear layer, like we could do this all gather for each of these linear layers individually. We could apply it at the attention layer and do the all gather for the 4 linear layers together. People typically do it at the decoder layer level. So we're taking the 7 linear layers and the 2 RMS norm layers and splitting them evenly across all the GPUs. The thing that you need to think about when you're figuring out where to put the all gather is how much memory and how often you want to be communicating, because this is like an all GPUs have to communicate everything. So that's kind of like the thing you need to be thinking about with all-gather. Okay, so for some code, this is just like a simplified version of FSDP 2. There's more details in the guide, but this got a lot easier with FSDP 2. The last time I gave this talk, it was way more complicated. So first, we initialize our model on the meta device, which I feel like, I don't know how many people know about the meta device, but I think it's so cool. It just like stubs out all the tensors and doesn't actually allocate anything. Then we can run fully shard on the decoder layers, which is a really simple API call now. Before it was like really complicated. And then because our model was on the meta device, we actually have to initialize it, which is this toEmpty call, and then we have to reset parameters. If you want to load pre-trained weights and broadcast them from rank 0, it's a bit more complicated, but check the guide. As far as I know, there's not like a lot of resources on it, and I actually found some bugs in FSDP, so if there's any PyTorch people here and you want to help me get a PR merge, that would be great. Okay, so let's do another live demo of FSDP. Okay, so first I'm just going to show the same exact command we just ran with 0 to show you the memory savings we get. So this is, again, just like 8 GPUs, Llama 8B with FSDP. I'll show you some code while we wait. But it's really pretty much straightforward. There's some things you have to consider with like CPU offloading, et cetera. I wrote this chapter for training Llama 405B, and I actually did test it with that. But yeah, so let me show you the NV top. So we're down to 40 gigabytes used. So DDP, we ran out of memory. DDP was 0, we had 60 gigabytes, and FSDP, we're down to 40 gigabytes. So that's kind of like the memory savings you get with these better algorithms. Okay, let's try to train something bigger, which basically is Llama 70B. I'm just going to go straight to, so if you try to train Llama 70B on a single node, you'll run out of memory. So I'm just going to show you multiple nodes. And with multiple nodes, it's a very similar torch run call. You just have to add a couple arguments, which I detail more in the guide. It's just detailing like how the nodes coordinate with each other. The other thing I want to say is I'm just running it manually for the purpose of this talk, but you should not do that. There's a lot of things you can do to schedule it automatically, so definitely don't do this at home. It's very risky. Okay, this is going to take a little bit to run, because it takes a little bit for the nodes to talk to each other. And yes, but it looks like it's starting to run. So this version of the code does load pre-trained weights, which it's talking about right now. And remember, this is Llama 70B, so we've like almost 8x'd our model. But we're only using 8 gigabytes to actually store the model, and that's because we've also doubled our GPU size, or doubled our number of GPUs. So we have, I don't remember how much GPU memory we have. Let's see our NV top here. Yeah. Okay, looks like training is starting. I also disabled torch compile for the purpose of this talk, just so we could get faster results, but you should not disable torch compile. Okay, it looks like I did not please the live demo gods and we got a bug. I'm so sorry, everyone. I thought this was foolproof, but you'll just have to believe me that it works. Okay, so let's keep going. Does FSDP scale to 405B models? So first of all, foundation models are humongous. Just some back-of-the-napkin math here. You need like 60 H100s to even like store the basic stuff, probably closer to like 80 to actually run something useful. I have run a 405B model with 64 H100s, and it was extremely slow. It was like 30 seconds per iteration, and I had to use CPU offloading. So you really need a lot of GPUs. The fallout of that is that all-gather operation that I showed, which is all GPU communication, becomes extremely expensive since it's n squared. Dang it, yeah, exactly right, everyone. Devastating, really. So what do? That's the n-dimensional parallelism. Okay, so Llama 4FAB was actually trained with 16,000 GPUs. So n squared all-gathers are insane at that level. And that's where the 4D parallelism comes into play. So all these other parallelisms are actually aimed at reducing the world size for the all-gathers. You can kind of see this graphic here from their paper. They have pipeline parallelism, context parallelism, and tensor parallelism, in addition to data parallelism. DeepSeek was trained with 2,000 GPUs and 3D parallelism. And this graph from their paper kind of shows their pipeline parallelism schedule. I actually think this is like such an interesting area for research, because if you notice these like white bubbles here, those are called pipeline bubbles, and that's when your GPUs are sitting idle. And it's really hard to design an algorithm with pipeline parallelism that doesn't have pipeline bubbles. And when you have 2,000 to 16,000 GPUs, it's very expensive for them to be sitting there doing nothing. So a lot of work goes into like actually doing all this stuff. So what are these other types of parallelism? So there's tensor parallelism, which basically splits your linear layers internal to a node across your GPUs. We have chapters on that. I could actually probably have time to talk a little bit about it. We have pipeline parallelism, where your model itself gets like split into different sets of GPUs. So like maybe the first 10 GPUs hold only the first 10 decoder layers, and then the next 10 GPUs hold the next 10 layers, et cetera. And that reduces the world size to basically 10. And then you have context parallel, which splits the attention. So yeah, that's actually, I really flew through this. I was very nervous. So if you have questions, I can also like talk about, I can do more with tensor parallel and stuff, but that's all I had planned.
I don't know if there's a microphone, but which, can you go back to the parallelism? Which ones do FSDP actually cover? Is it only pipeline parallelism, or is it tensor parallelism and context?
So FSDP is different from all of these. So FSDP is a data parallelism technique, and so is distributed data parallel. And these kind of like fit in line with that. So you can use all these with FSDP. So we have a chapter showing how to use tensor parallelism with FSDP. You really need to scale up to like at least 100 GPUs to see like a benefit from tensor parallel, because there's like a overhead with using it. So yeah. Mm-hmm.
How does it work with the MOE model?
With MOE model, so MOE model training, I think it works very similarly. I don't think it would work any differently for, the question was how does FSDP work with mixture of expert models? So it's gonna work the same no matter what type of model you're using. You're still gonna be sharding your mixture of experts like over all your GPUs and then doing an all gather. I am guessing that there's probably some optimizations where they don't have to gather the experts that aren't being used, but that's probably like a very specific training pipeline that I don't know. I don't know if Torch Titan does that or other places, but there's probably some optimizations, but mostly it works the same. Mm-hmm. Oh, yep. Sure, yes. I will show you some code for that. So let's kill this. So loading from pre-trained is a bit weird. There's this API set model state dict that PyTorch has, where basically on rank 0 of all your workers, so GPU 0 basically, you load the full model weights in CPU, and then this set model state dict will broadcast that basically to all the other ranks. There's currently a bug with this where it doesn't broadcast buffers, if you're familiar with like PyTorch modules. So you have to do some extra stuff to broadcast the buffers. Otherwise, things like layer norm won't properly work. I did not realize this for a while, and my training was stalling. And I was like, what the heck's going on? But yeah, that is how you do that. So does that answer your question? Cool. Okay. Any questions? Okay, I love that. Oh, okay.
What's the overhead of SFTP at like 8 GPUs?
At 8 GPUs, FSDP is like really, there's not a lot of overhead. The all gathers are really fast, especially when you're at 8 GPUs on a single node. Inter-node, inside of a node, communication is much faster than outside of a node. So there's really very little overhead. And that's why people do tensor parallel inside of a node, because there's a lot more overhead with tensor parallel. But yeah, at that size, FSDP should be great. Oh, yeah.
Can you talk a bit about like data loading when you're doing DDP or FSDP?
Yeah, sure. So pretty much for data loading, all of your GPUs need to have access to the full data set. This is more like an environment thing, but for most distributed training setups, you have like a shared drive where you have your Python environment, all your data, et cetera. And so all your nodes have access to like the same exact Python code and your data. And then the only thing you have to do differently, I actually deleted this slide, maybe I should have kept it in, but let's see, oh yeah, here it is. So there's this distributed sampler class. So you basically just add that into your data loader, and then that's all you have to do. It's really easy.
What if you have like sharded data?
Sharded data is a bit of a different case. In that case, like, are you saying if every GPU, if the data on a node is different from data on another node? I think in that case, you would probably have to come up with a slightly different, they might have a sampler in PyTorch, honestly, but honestly, in that case, you might just be able to use data loader by itself, just with some, you might have to do some like data wrangling, like you might have to do like train data and then like modify it for each rank on the node itself, because there's still 8 GPUs typically on a node, so you'd have to figure that out. Yeah. Yeah, I think there are probably better people to answer that question. Typically with Lambda machines, when you get a cluster, they're kind of like all set up already. Plug for Lambda. Okay. Oh yeah, we can't pause. Yeah, I definitely get that. Definitely get that frustration. But yeah, I think there's something I used to have to do. I'll just give this tip, but there's in like I think it's SSH authorized key, or no, I think it's authorized keys. Sometimes you need to add your SSH key into. Let me not show. Well, there's a public anyway. Sometimes you have to add your key into both machines to make sure they communicate properly, but yeah, they should be pretty much set up properly. Okay, I think we have time for like maybe like 1 or 2 more questions. I'm loving these questions, everyone. Oh, sure, yes, the link. Let me show the QR code. Yes. Plug for the tensor parallel and 2D parallel chapters. I found some pretty good graphics to explain them. I think tensor parallel is a little bit hard to understand, especially when you talk about 2D parallelism, so definitely check out and give me a star. Okay, any last questions? You got 30 seconds.
Do you have context parallel if you're distributed training?
There's no context parallel. The PyTorch API for context parallel is still in like pre-alpha. So, I mean, if people are interested, I can add like the alpha APIs. I think pipeline parallelism is still in alpha too, but I can definitely add that. I'm seeing some nods, so cool. All right, I'll end there. Thank you, everyone.